All right, welcome in. This is our quick overview of chapter 6. We're going to introduce moles, we're going to introduce molar mass, and we're going to show a strategy for solving some kind of calculation style questions. All right, so here's our plan. We want to be able to quantify the number of atoms or molecules that might be present, but if we're thinking about regular sized objects, there are going to be billions and billions of atoms, billions and billions of molecules. That makes it hard to kind of quantify how much of these very, very tiny things might be present in our everyday scale objects. But we can group things together to make our life a little bit easier. And maybe we've done this before, right? If we talk about things in terms of dozens, we know that a dozen refers to 12 of something. And it actually doesn't matter what we're talking about. We could think about a dozen of those things, right? If we have cupcakes, those can come in dozens, or roses we can buy by the dozen. Golden retriever puppies here. Maybe they don't usually come by the dozen, but we can think about a dozen of whatever we want. And no matter what, it's always 12 of that thing. This makes our life a little bit easier. If we're trying to order, flowers for a banquet, we can count by the dozens. If we're ordering, food for a lot of people, we can order dozens of desserts. Or maybe if we just want a lot of puppies, we can order, or we could visit our puppies by the dozen. In chemistry, we need bigger groupings because we have many, many, many more of our atoms or molecules. But it's the same idea. We're going to have groupings of things. Our grouping in chemistry is known as a mole, and it's defined as 6.022 times 10 to the 23rd of whatever we want. It's a grouping of this number, just like a dozen is a grouping of 12. We can abbreviate this number as Na. It's a little bit easier than writing that number out all the time, but that's what it is. It's 6.022 times 10 to the 23rd. A grouping of this many things. We can think about what this grouping means. Well, it's this humongous number, right? Scientific notation is our friend when we have this enormous kind of number. And it's the number of items that are contained in a mole of that thing. If we're thinking about groupings of objects, it depends on what the object is. In terms of carbon atoms, well, 1 mole of carbon atoms is 6 times 10 to the 23rd carbon atoms. 1 mole of maybe helium in a balloon would be 6 times 10 to the 23rd helium atoms. Turns out it fills up about a regular sized balloon here. A mole of carbon atoms might be, a handful of carbon atoms. A mole of sand is this many grains of sand. A mole of puppies would be 6 times 10 to the 23rd puppies. Many, 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 many puppies. More than exists in the universe, but we can at least think about it. I encourage you to think about it because they're very cute. For more real life things, 1 mole of copper atoms is pictured here down at the bottom right. Turns out our copper atoms are about, what is this, about 22 cents. If we want 6 times 10 to the 23rd copper atoms, that's contained in about 23 pennies. Cool. Notice here our Avogadro's number is units of things per mole, or sometimes it's written just as units of 1 over moles. But we can use this as a conversion factor to figure out, well, how many objects we have if we have a certain number of moles. Or if we know how many items we have, we can figure out how many moles we have. And so we can do some calculations like that. It's a useful conversion factor for the number of things to the number of moles. Okay, switching gears a little bit. What if we want to measure things based on their mass? Measuring mass is really straightforward in a lab. You can put things on a scale and get a mass measurement very easily. Unfortunately, if you have different objects, they're going to weigh different amounts. It's not groundbreaking here, but if you have a dozen puppies compared to a dozen roses, well, the puppies are going to be heavier than the roses. Same thing with our moles. If we have Avogadro's number of puppies and Avogadro's number of roses, they're going to weigh different amounts. We can define this as our molar mass. How much does something weigh if you have 1 mole of it? So if you have 1 mole of puppies, how many grams does that weigh? If you have 1 mole of carbon atoms, how many grams does that weigh? Right. How much does it weigh if you have exactly 1 mole? And so our units here end up being grams compared to moles. Conveniently, on our periodic table, the number that is the mass of 1 atom in units of AMUs is the same number for our molar mass in terms of grams per mole. So these end up being numerically equivalent. They're the same number, just different units, based on our definitions of moles and our definitions of atomic mass units. So here, if we have copper, we can look up on our periodic table. We look up copper. We see this number, 63.55 at the bottom. This 63.55, it tells us 2 things. It tells us if we have 1 atom of copper, this weighs 63.55 AMUs on average. And if we have Avogadro's number of copper atoms, this weighs 63.55 grams. Or in other words, the molar mass, which I like to draw as this cursive M for copper, is equal to 63.55 grams per mole. Pardon the pen here. If we look at the periodic table for hydrogen, the number at the bottom is 1.01. Again, this is the mass of a single atom in AMUs, or the mass of a mole of atoms in terms of grams. Here we have some pictures, right? If we are thinking about how much something weighs, well, how much does a dozen of something weigh? Depends on what it is. Same idea for moles. How much does a mole of something weigh? Well, it depends on the substance. So looking at our periodic table, sulfur has a molar mass of 32.07 grams per mole. And so here we have a dish of 1 mole of sulfur atoms. What this means here, our big note, is that we need our periodic table to help us figure out, well, grams converting to moles or vice versa. We need that molar mass off the periodic table. All right, our summary, our molar mass. Again, I'll try to abbreviate this with a cursive M. This allows us to convert from moles to grams or vice versa. Avogadro's number, which we have as Na, allows us to convert from the number of moles to the number of things, right? Because we have these units, we have this ratio of grams per mole, or we have this ratio as the number of things per mole. We like this unit of a mole, we like this grouping of a mole in chemistry is almost like our home base. Finding the number of moles that are present is going to be a great first step for about 99% of the problems that we'll see. It's almost like the trains in Los Angeles. all the trains go to Staples Center, go to LA Live. And so if you want to get somewhere, great, go to LA Live, that can be your home base. And then from there, you can go wherever you want. All right, it's our central point, it's our central hub, where we have many ways to find how many moles are present and many ways to find other units that we might want, starting from moles. Here's a generic 3-step plan that will really work for, again, like 95% of the calculations that we'll see. Step 1 can be find the number of moles. This is our home base. Let's get to home base. Our second step, maybe we have information about one chemical, but we care about something else. Hang tight for 1 second. We'll get to that in the next slide. And then lastly, we can convert back to whatever unit that we are asked about, from moles to something else. So here are 2 things. We can go from grams to moles using our molar mass, or we can get from the number of things to moles using Avogadro's number. If we can use something in step 1, we can also use it in step 2. We can go from moles back to grams using a molar mass. And we can go from moles back to the number of objects, atoms, or molecules using Avogadro's number. There we go. We'll look at an example in 1 second. But first, let's think about the second step. Can we convert from one substance to a different substance? Well, we have one way to do that. Maybe we know some ratio based on the structure of our substance. So looking at something in the macro scale, if we have a 3-leaf clover, we know that we have 1, 2, 3 leaves for every one of our clovers. 3 leaves for every 1 clover. This ratio can be phrased as a conversion factor, right? We can write this as 3 leaves per clover, or 1 clover per every 3 leaves. And so, yeah, we can build these conversions. If we have 14 clovers, and we want to know how many leaves there are, we can use this first version up here, 3 leaves for every 1 clover. 14 times 3 is 42. We have 42 leaves for every 14 clovers. We can convert from one substance to another if we know something about its structure. Same idea with our chemical formulas. The subscripts in our chemical formulas gives us the exact same style of information. It gives us information about the structure. So here, if we have, I don't know, CCl4, we can count up these atoms. 1, 2, 3, and 4. These are our chlorines. And then hiding in the center, we have 1 carbon. So yeah, sure. We can have this ratio of chlorines compared to our molecules, or chlorines compared to our carbons. Right, so we can use these subscripts values to build our conversions. All right, there we go. This kind of wraps up our plan. We can convert to the number of moles. Maybe we can use our chemical formulas to switch from one type of substance to another. Then we can get whatever unit that we'd like. These are the tools we have so far. As we continue on in our chemistry careers, we'll add more tools to find new ways to get the number of moles present, or new units to convert to out of moles, and new ways to switch from one substance to another. But this 3-step plan down at the bottom, this is going to be really good for about 95% of our problems. Here's one example right now. If we have a diamond necklace with this many atoms of carbon, how many grams does it weigh? Well, we know the number of atoms. We said maybe the carbon atoms. We know our home base is going to be moles. So can we get the moles of carbon? And then from here, we're talking about carbon. We're thinking about how many grams it weighs. All right. Can we get back to the unit that we are thinking about? Grams of carbon. This gets to be our roadmap. 2 steps. One is the number of atoms to the number of moles. Seems like an Avogadro's number calculation. The second one is moles to grams. Seems like a molar mass calculation. So let's set it up. 15.0 times 10 to the 24th atoms, carbon atoms. Going to have 2 arrows, means 2 fractions. All right, let's cancel out the number of carbon atoms. And let's figure out the moles of carbon. This ratio, I recommend, let's just put a 1 next to the mole. Right, we have mole of carbon somewhere. Let's put a 1 next to that. And then we can ask, okay, if we have 1 mole of carbon, how many atoms is that? Well, we always have Avogadro's number of things in an atom, things in a mole. So 6.022 times 10 to the 23rd atoms for every 1 mole. Our next step, we want to not stay at our home base. We want to cancel out moles of carbon, and we want to figure out how many grams this weighs. So again, let's put the 1 next to our unit of mole and say, okay, if this fraction needs to make sense on its own, if we have 1 mole of carbon, how many grams does that weigh? Well, this is our definition of molar mass, and we can look this up off the periodic table. In this case, it's given to us right here. 12.01 grams of carbon for every 1 mole of carbon. Different things weigh different amounts, but for carbon, this is what it is. We can check our units here. Carbon atoms cancel out. Moles cancel out. Grams is left behind. Punch this into the calculator. Probably 3 significant figures. $299 grams for our carbon in our necklace. And there we go. That's our plan. That's our strategy. Here's our example calculation. Again, we'll continue to have these new tools added, but this is the idea. Moles is our useful grouping of objects. It can be our home base for these kind of chemistry calculations. Thanks for watching. See you all soon.